Hello everybody and welcome to our introduction to computational fluid dynamics final presentation. CFD or computational fluid dynamics can help you solve complex fluid mechanical problems. There are many CFD software tools that can yield similar results. Some of the software that you can actually use to yield these results include ANSYS, which is a software that we use for our class specifically and is very beginner friendly, Fortran, OpenFOAM, CFX, and COMSOL. It is important to note that certain softwares like OpenFOAM can allow one to write a code. This is specifically for people that understand and know how to write code. Otherwise, it could actually make you waste a lot of time. Moreover, using CFD analysis, certain physical properties can actually be studied, which include velocity, pressure, and temperature distributions. There are many reasons why computational fluid dynamics is very important in the engineering world. The first reason is that it's a cheaper alternative way to develop new prototypes, which in turn can save companies a lot of money. That being said, it will also provide flexibility. This means that engineers will be able to quickly modify or redesign a certain product and rerun tests quickly without spending much time and getting quick results. CFD can also provide precise data that would be nearly impossible to calculate by hand. So instead of sitting there just calculating several problems, just wasting a lot of time using the CFD software, you will be able to quickly find results that you need without killing any more time than you need. CFD, specifically the tool used, or Fluent, can be used for any problem where a fluid is being involved. So if you have any sort of pipes or you need to calculate any problems where you have to analyze a pipe, this would be a specific tool that you can use using ANSYS. Computational fluid dynamics can be used in a variety of fields that involve the flow of a fluid over or through a body. There are several fields where this can be used, which include the aerospace field, automotive, power generation, chemical manufacturing, where they process specific polymers, medical research, and many other more applications that were not listed. For the specific problem for the group, we decided to simulate the airflow patterns inside a computer. The goal was to display the mechanical properties within the case, which included velocity magnitude, velocity vector, and temperature distribution. There were four main components that were essential to the simulation, which included a Corsair Obsidian RGB tower case, which was able to have four fans installed, 120mm Corsair WL series fans, four of them specifically, a GeForce GTX 1070 graphics card, and an Intel i7 6700K processor. The graphics card and the processor were essential for the project specifically because they will be able to exert a certain amount of temperature within the case, which would in turn heat up the air within the case. The point of the fans is specifically to provide colder air, which will in turn cool down the GPU and the processor, and then the air will be able to exit through the backside of the case with the fourth fan, which had a certain velocity.
So like mentioned before, we use four fans, we use a CPU, a GPU, and a case to construct our geometry. As you can see on the top and the bottom, on the right side, there's three fans, and then the two components in the middle is a CPU and GPU, and the one component at the end is the outlet fan, which is in the left top corner. Since this is a 2D model, thickness was excluded. If we're to use thickness, then this would instead turn into a 3D model, so we try to avoid that and kind of just keep it basic. We also provide the in-depth specs of the components by giving you the measurements in inches. Okay, so for our mesh, we did an all triangle method. We refined it to 3, and we used an element size of 0.0025. Along with that, we also name a couple of components. So the three right on the right side are called the inlet fans. The one on the left side is called the outlet fan. The components down the middle are the CPU and GPU, and the case is considered here as the walls. As you can see from our mesh, is very very thin. That's also because we used a smooth and fine selection when we designed the mesh. Okay, so for our setup, we first started by stating our boundary condition. For our boundary connection, we label the inlet temperature coming in as 300 Kelvin, which is room temperature, and the fans, their airflow, the fans coming in was at 2.52 meters per second. We also gave a temperature to the GPU and CPU. The temperature for the GPU was 343 Kelvin, which is a normal temperature. It's not at a high temperature or a low temperature. And the temperature for the CPU was 323 Kelvin. For our setup, we also turned on the energy equation, the K epsilon equation, and we set our time to transit. Along with that, we used a fluid of air. We solution analyzation, we calculated at the inlet. So as you can see, since we're doing it from the inlet, our x velocity is negative 2.52. That's only because it's going from right to left on the geometry. So, velocity is going from right to left will be at a negative x direction. And then our last step was to run the calculation, which we made a 1,000 time steps, and it recorded at every 3 time step. That's why we have a 3 time step size. And then we also had a max iteration of 20. Alright, so once we ran the calculations, then we got the results. Here we show 3 graphs. The one on the left side corner represents the temperature contour, the one on the right represents the velocity contour, and the one in the bottom represents the velocity vector. We're happy with the results, and we could see the change in temperature distribution in our left side model. And then we could also see the airflow patterns on both the top right and the bottom right. The bottom right basically is just an in-depth velocity distribution over our model. We use a cone, 3D cone, to kind of see a better in-depth view of the way the arrows are pointing. So to kind of get a more in-depth, we decided to do animations on all 3 graphs. So the one on the top left, of course, like explained before, is the temperature contour. So if you could see the velocity airflow being reached from the fans and causing a change in temperature distribution all over both the CPU and the GPU. For the one in the right, you could see a velocity flow being shifted all over this PC. So you can see the velocity entering from the right side and exiting at the outlet fan. That's where the orange and red area is at. And for our last graph, we animated the velocity vector of the PC. So we use a 3D cone just to have a more in-depth view of which way the arrows are going. And you can see the same as the velocity contour. It starts from the right and is exiting at the exit outlet fan. And you can see the arrows pointing red. That's a good sign that it's leaving the PC. So it's going from right to left, reaching the GPU and CPU, and exiting. So it's great news for us. So for a fun element, we decided to go over a YouTube video that we found online. Um, let's play this over. So kind of like our design, there's cool air trying to cool off a PC, the GPU and CPU. So you can see the flow of air coming in from the right and exiting from top and left. Now it's exiting from the top because they have a fan connected at the top of the case. For ours, we just had a fan connected on the left side of the case. So this is kind of like what we did. So this shows an excellent representation of what we designed, and their results came out almost identical to ours. So to conclude, we first start by saying that CFD provides excellent tools for real world problems that deal with fluids. Uh, if you're trying to run a CFD analysis and try to find like velocity contours, pressure contours, or temperature contours, a great tool to use is ANSYS. ANSYS is beginner friendly. You could use it and learn on the go as soon as you open the software. Uh, it's a great tool to use, and many companies use it. So companies use a CFD tool for what? They use it to run the simulation before they decide to make a product. So if you're making a pipe and you're sending fluid from one end of the pipe to the other end, and you're trying to see what temperature distribution or what pressure distribution goes along that pipe, you can't just make a random pipe and just say just make it this dimension and see how it goes. You have to use a CFD analysis on it to one to see if the pipe will perform well. And well, how would you do that? There's many programs out there, but the ones that we have learned are answers. That's just one of them, but it's an excellent tool to design the product, and then once you're happy with the results, you could finally say the okay and design it. And that's what CFD analysis is for. It helps you do design that product. So for reference, we use Ansys 18.1 software to design our PC. We use online sources such as computational fluid dynamics and cardthrow.com to help find issues that we're having, such as calculating for the velocity of the fans from RPM to meters per second. Along with that, we also use online sources to find our specs for our components, finding the size and finding the average temperature for CPU and GPU. And that's what we use to basically build our model and design our model as well.